Vacuum tube computers are really fascinating machines. They do some things almost identical to how we're still doing them on modern processors today. And then they do other things that are just dramatically different. And well, that's because vacuum tubes have a lot of really interesting limitations associated with them. But I actually have two vacuum tube computers in this room. The first one is this one over here on my right. It's the UE1. This is a homebrew vacuum tube computer that I've been building from the ground up for a couple of years now, and we're really close to coming to completion on it. And the other is this machine right here. This is a Bendix G15, a full-fledged vacuum tube computer from 1956. Although this one is serial number 238, so it's probably like, I don't know, 1957, 1958, somewhere around there. But this machine has a really fascinating history behind it. It was developed by Harry Huskey, and he worked with Tommy Flowers and Alan Turing on multiple projects over there, including Alan Turing's Pilot Ace. And a lot of the design decisions that Turing put into the Pilot Ace found their way into the Bendix G15. So there is a direct link between this machine and Alan Turing himself, which makes this an incredibly historically important machine. And as far as I know, there isn't a running G15 anywhere in the world. And if we do get this machine running, it could very well be the oldest running digital computer in North America. That's pretty insane. So how did this machine, this historically important machine, end up here in this room with an idiot that barely knows how to swing a hammer? Well, this one is on loan from Bob over at System Source Museum. And if you haven't heard of System Source Museum, go check them out immediately. It's one of the greatest computing history museums in the country, bordering on one of the greatest in the world. Bob is one of us, 100% one of us. He's super passionate about these old machines, and he really wants to see them come up, because not only can we learn a lot by how they were built and designed, but we can also learn a lot by sitting down and using them. And that's exactly why Bob sent this G15 all the way down here to Texas. So we could get it up and running, and once it is, we can send it back up to Maryland so it can go on display at System Source Museum, and they can fire it up and give displays, and people can get hands-on with it. You guys could get hands-on with this machine at System Source Museum whenever it's working, because currently it doesn't work. Whenever we spin it up, you flip the go switch and absolutely nothing happens. Totally inert. So our goal today is to try to get it to execute at least a single instruction, because I promised Bob that this thing would be executing instructions before the end of the year. So if we can get it to execute one, I think that technically fulfills my promise, but I would like to see it execute more. And honestly, I think if we can get it to execute a single instruction, getting it to execute 2 instructions or 10 instructions or 20 instructions shouldn't be too much more effort beyond that, because I think the way that the machine is designed is that a large majority of it has to be working for any of it to function at all. So we got a lot of work to do. Lloyd is coming down, and we're gonna just hunker down and try to hammer out all of the problems that we can come across and get this thing at least showing some signs of life. So it's going to be a pretty exciting one. Let's get started. All right, first things first, let's double check a couple of things, starting with, is it where we left off last time? And in order to check that, we're gonna look at it on the scope here, but you may notice that the scope has changed. This is a beautiful Keysight 4-channel scope. And how this ended up here is a pretty wild story. I was talking with a good buddy of mine, Avery, and I was really lamenting that I didn't have a 4-channel scope. And he said, hey, you should just reach out to Keysight and see, you know, what's up. And so I did, and I sent an email to Keysight, and they really loved that we were working on the Bendix, and they thought it was awesome, and they sent this amazing scope out. So this is now my primary scope. You're gonna see a ton of it, and we're really gonna put it to work today because it's got 4 channels. I wanna look at 4 separate tracks on the drum and see what's going on. But like I said, first things first, let's see if it's where we left off. So I'm gonna push the reset button here. AC's already up. it clicked off. The tape is now reading. We can see data filling in, pushes off to the right like a shift register, like it absolutely should be, comes around from the left. That is the number track successfully copied over onto the drum. It's going again. Now it's copying over the first track of diaper. We get up to there, the tape has stopped reading, we got our click. DC is fully up, we're ready to go. So if I flip the go switch on the typewriter over here, nothing happens. The machine is totally inert. So we have a failure in between the go switch and the machine actually trying to go. And I've got Lloyd and our other good buddy Troy down here today. We're gonna do some serious work on this thing. So, well, with our new tool here, it's gonna be a fun day. The problem is that when we flip the go switch, nothing happens. So let's look at the simplified diagram and follow the go switch in from there. And coming from that switch, we hit a lot of logic. If I'm following this right, we go through a buffer inverter, then to the CZ flip-flop, which then goes to another AND gate, then an OR gate, and finally into the CJ flip-flop. Now we do actually have an idea of what the CJ flip-flop should look like. It's drawn right here for us. So this seems like as good a place as any to start. And so now we need to move over to the real deal schematic now, which is a nightmare to try and read. But we can find the CJ flip-flop in the bottom left here. It's looking like it's pack J23. I'll hunt that down on the back side of the doors and hook my probe up to pin U. And looking at the scope here, we have a single short pulse. I'm not sure if the timing of that is on point yet, but that's good enough to move on to the next step in the process, I think. Coming out of the CJ flip-flop, we have a few directions we can go, but ultimately we want to work our way towards the RC signal. The RC signal is a command to the rest of the system to start reading in a command. So heading in that direction, we cut through another AND gate, then to an OR gate, and finally into the CK flip-flop. The flip-flops are good landmarks to do checks on, so let's check this flop. Back over on the real deal schematic, it's easy to find because it's right next to the CJ flip-flop and looks like it's also pack J23. Pin S is the pin we're looking for, so I'll just move the lead over to that one. And looking at the scope, yeah, we got squiggly lines. That's good news. All that's left before the RC signal itself is this 3-input AND gate here. One input comes from the CK flip-flop, one from the CL flip-flop, and one from the CQ flip-flop. But if we look at the schematic, there is actually one more stop on the RC line, and that is this buffer right here, J25. So let's check this buffer just to be safe. I'll move the clip lead over to pin R, which is the output from the buffer, and looking at the scope, yeah, that's weird. We have what looks like pulses, but they're petering out at a negative 10 volts max. We should be seeing a full negative 20 volts to 0 volt pulses here. Zooming in on the weird pulses, and it's absolutely bonkers. I can't make any sense of this output. Let's get a second probe hooked up and compare input and output. This will tell us if the buffer is the issue or the AND gate. And looking at the scope again, yeah, that's properly messed up. This epic Keysight scope, though, has more channels. So let's put some of those extra probes to use and look at all 3 inputs to the AND gate simultaneously. I've staggered the 0 volt levels of the inputs by 1 division here, and we start with 2 of the inputs high at 0 volts. The yellow trace input is low at negative 20 volts until I hit the go switch. Then it starts pulsing between negative 20 volts and 0 volts. Which means that we have a moment in time where all 3 inputs are 0 volts or high. So the output should be pulsing exactly like that, but that isn't happening. So that means that the AND gate is bad, right? Well, if only it were that easy. We pulled that AND gate out and swapped a different pack in, and no change. And then I tested that AND gate on the diode checker, and all the diodes tested out fine. So the AND gate is fine, but something is pulling the output of it down. And in order to understand why or how that can happen, we need to take a look at the schematic for how an AND gate is made. And these big schematics are, like, first of all, a nightmare to read. They're almost impossible to follow. but also they just draw AND gates as the logic symbol. So you can't really actually see how the individual diodes and resistors are connected to each other. You got to kind of infer that by looking at this and then looking at the individual schematics for the packs that are used. And well, that's that's a nightmare. So I just sat down and spent some time redrawing that whole area right there. We've got our three inputs, CK, CQ, and CL. These should be toggling between 0 volts and negative 20 volts. So 0 volts is logic high, negative 20 volts is logic low. They all connect together on the backside, and they have a 110 k ohm pull up to plus 100 volts. Now, if all three inputs are low at negative 20 volts, there is a path from plus 100 volts through the 110K down to minus 20 volts. The output that we're seeing is essentially going to be negative 20 volts. If all three inputs go high, they all go up to 0 volts. There's still a path to 0 volts through these diodes, but there's no longer a path to minus 20 volts anywhere. So the output that we're seeing here is pulled up by the 110 k ohm resistor to 0 volts, but we're never seeing that 0 volts. So where does this output go from here? And it goes to three different places. It goes to another 2 input AND gate over here on the right, and then it goes down and splits into 2 cathode follower buffers. Now these cathode follower buffers have voltage dividers on them that go between ground and minus 160 volts. But the voltage dividers are massive, 560K and 750K. And initially this is kind of where we thought our problem was. We thought maybe one of these resistors had gone bad or gone to short, but we swapped the buffer packs out, didn't make any difference. And here's where we lost about 5 hours. I had Lloyd here, I had Troy here, two of the smartest, most brilliant engineers I've ever met, and the three of us were well and truly stumped for hours on end. There's some pretty tricky electrical engineering stuff going on here that's a little difficult to follow, particularly because vacuum tubes are strange. But since we didn't figure out while they were here, they had to go home. It was like 7 p.m. and they had to load up and head back up to Dallas. So I ran inside after they left and ate a quick dinner, and then I came back out and I fired up the laptop and hopped on the Discord with a live chat with all the guys over on the Discord and got back to work. And I spent another 4 hours on this thing. I was dedicated to figuring it out. And ultimately, we did manage to get it to do something. You can see here in this footage supplied by Avery that when I flip the go switch with my foot, we do actually get some changes in the neon lights, and I think that means it executed its first instruction. So what did we do to get it to do that? Well, the confusing part here is that if you look at the schematic, the output of that AND gate only goes 3 places. We essentially eliminated these cathode follower buffers as being bad because we replaced the pack multiple times, and so that kind of limited it only to this other AND gate. But we replaced that pack multiple times and double-checked all the diodes, and it was fine. So where was our draw coming from? Well, we got desperate and started grasping at straws, and I started replacing packs on the other side of the cathode follower buffers. Now, this should have absolutely, positively zero influence because the cathode and the grid are not connected in any way. There should be 0 grid current here. And I replaced the like 7 or so AND gates that it goes to on the other side of both of these cathode follower buffers, and yeah, no change. Replaced them all with different packs, tested all the diodes, absolutely no change. Did not affect the output positively or negatively in any way, shape, or form. But there was one more connection on the other side of these cathode follower buffers that I had missed. And that's because if we look at the schematic here, there's one little wire here that says RC, and then it has 1G and some other stuff in parentheses next to it. That's telling us that that signal goes to a completely different page. And that page is this page right here. And we can see that that signal goes into a OR gate that ultimately feeds into another flip-flop. And that OR gate is diode pack A10. And so finally I discovered that, I pulled A10, I swapped it with another diode pack, and all of a sudden our AND gate came screaming back. What on earth is going on here? Well, it turns out that Grid leakage current is a real thing. And so if we had a problem on that diode pack, it could be putting enough of a heavy load on that cathode follower buffer that we are actually starting to see some grid leakage current. And if we see any current leaking through the grid on that tube, it's going to directly affect the output of the AND gate before it. And that was something that, honestly, this is the first time I've experienced grid leakage to the point of breaking an AND gate. So that was a really eye-opening moment. But what happened to that AND gate, the A10 that we pulled out there? Well, if we look at it on the diode tester here, it tests totally fine. So I think it's safe to assume that the diodes themselves are going to be fine. But if they're fine, what else is there? Well, after closer inspection, it looks like we have a solder bridge. This is interesting because this pack has all original diodes, and it's one that I didn't do any rework on, so this is a leftover from Bendix, probably. Anyways, after clearing the bridge, things went sideways yet again. We were no longer successfully reading in data from the paper tape. We're going backwards here. This was, again, another solder bridge, but this time it was actually my fault. It was on a pack that had been swapped out multiple times in our earlier troubleshooting efforts, and I had ultimately moved it to a vital part of the boot up process. Hours later, we were able to hunt down the proper pack and clear the solder bridge, but the machine still would only execute just a single instruction and then halt. So let's try to confirm if the single instruction is accurate. The diaper manual has an instruction listing in it, and the first instruction is a copy from line 19 to line 0, both of which are available on the test panel on the side. I have the scope hooked up with 3 probes here. The green is T0. This is a single pulse at timing point 0 once per revolution. Yellow is line 19, and it's full of the first block of diaper that was read in by the paper tape. Blue is line 0. Right now it's full of junk left over from boot up, but when I hit go, it should get an exact copy of line 19 in it, and it doesn't. It looks like it clears out to be nothing but low, but that's not actually entirely accurate either. Looking farther down the line, it looks like words 17, 18, and 19 copied over faithfully, and absolutely nothing else. Okay, so let's see if the transfer and read command signals are happening correctly. We're expecting RC and TR to do, I don't know, something. In this scope shot, again, yellow and green are line 19 and T0 for triggering. Blue is transfer and red is read command. And I saw a short blip on red, and blue went high and stayed there. But that's at T0. Let's move forward to our word 17, 18, and 19 area. And we can see that the TR command goes low and the RC command goes high. The timing of when these happen is all broken, but the signals themselves look good. All right, I think this could potentially be related to source and destination. If we go back to the front panel neons, when we hit go, the source changes to 21, but the destination stays at 0. If we look at the instruction, when the source goes to 21, the destination should change to 31, which is a special location used for specific stuff, and I don't need to focus on that right now. The important part is that it never becomes 31. An instruction is split into 2 halves, a dynamic and a static portion. The static portion is the side we care about now because it contains the 2 characteristic bits, the 5-bit source, 5-bit destination, and the single or double precision bit. This static portion of the instruction is held in a large shift register that is composed of 13 flip-flops. And this is one of the reasons that tube computing is so difficult. You can see that just having a 13-bit shift register, this is something that is extremely trivial with 7400 series logic chips, takes up 13 flip-flops. That's like 6 packs on the door. That is a not insubstantial amount of real estate in that machine. And so, man, tube computing is just hard. Sometimes there's absolutely no way you can get around just having to use a bunch of tubes, which is exactly what they're doing here. But at any rate, our shift register here is at least half working because the source bits show up correctly. But things are supposed to shift left to right, and if there's a fault between C7 and C6, that could prevent the shift from continuing on down the line. In this scope shot, we're looking at the input to C7 in green and the output from C7 in yellow. And that's not good at all. We have wibble wobbles on the input and nothing on the output. Time to go inspect the C7 flip-flop. And sure enough, we've got a bad filament. One half of the tube is not working at all. That's definitely going to cause a problem. And interestingly, swapping the tube didn't fix it though. So let's move down the line to the next flip-flop, C6. In this scope shot, we're looking at the input and the inverse input to C6 in blue and green, and the output is in yellow. Again, we have wibble wobbles on the input and nothing on the output. The tubes on C6 are fine, so let's pull the pack and see if anything jumps out. And wow. Yeah, all right. Someone has modified this pack. Somebody sliced the leg off of this resistor and modified another resistor. That absolutely would cause a problem. I have a few spare flip-flop packs, so let's just go ahead and swap that out. Okay, so far we've found a bad tube, a destroyed flip-flop. It looks like somebody lifted a resistor on there. That's really strange. I have no idea what's going on with that. And we found 2 solder bridges, but we haven't found any bad diodes, so that's a pretty good indication that the Bendix diode checker is doing what it's supposed to do, and we pretty much sussed out all of the nasty ones in the previous episode. So I'm thinking there's signs of life here. I'm gonna hit the go switch and just go for broke. Hopefully we execute more than just a single instruction. Here goes nothing. It tried it tried to print. It tried to print, but the platen is so long it ran into the wall. But the typewriter did stuff. Pretty monumental. It just ran code. The Bendix G15 just ran code. Now let's take a minute and try to figure out what exactly happened. All right, what just happened? Aside from the fact that my 28-inch platen just tried to punch a hole in the side of my bookcase, which is hilarious. But I think we just executed far more than just one instruction. It seems like we got pretty far down the line. And if we look through the diaper manual, we have a list of the assembly instructions that are going to be executing on the machine. So let's follow this through and see if we can figure out what just happened. The first instruction is a copy of line 19 to line 0, and the second instruction is also a copy of line 19 to line 0, but it's if test is set and test is not set. But I can see that on the first instruction, we jump to instruction 2, which skips over that second instruction. So, and we're already doing like a branching jump here, which is pretty impressive, the fact that we got past that. The instruction after that is stop DA1, then we've got a clear, then we got clear line 18, then we've got a copy of number track to line 18. And then here's where things start getting interesting. We clear and subtract the value 147X86W from the accumulator register. And then we add all of that to line 18, and then we do a 0 test of the accumulator register. If I understand this correctly, this is doing a checksum calculation and comparing it against the value of that first block of code from the diaper. So if the two checksums don't match, it knows that the first block of code that was read in from the diaper is a problem, and it's going to branch out and start printing error stuff, which is what the next couple of instructions are. So we're going to skip over 14 and 35 and jump down to 13. Now, if you're wondering what these numbers are and why they don't make any sense, these numbers are locations on the drum, and it's just going to that location to execute it, because each instruction has a go-to in it. But if we take a look back at number 13, it says number track checks, and then it has a bunch of ones to AR. Seems like we're still doing some more checksums, but this means that we're loading values in, and we're doing addition, and we're doing subtraction, and we're doing all sorts of really fantastic, complex stuff here. And if it is a non-error, we're gonna go all the way down to 27. Then we go into read tape, which we see it do. It actually reads in the tape. Then we clear and subtract summation of interrogator from AR, we test ready, we copy line 19 to line 5, we add all line 5, we do another 0 test on the accumulator register. If that is all good, we skip down to 68, so we skip some more error codes there. We do an interrogator summation check, and then we clear line 23, and we get to gate type in. Gate type in is where we've now halted, because it is waiting for input from the user. So that's something like 50 instructions with multiple branches, and it all executed it perfectly, and it's waiting on input from the user on the typewriter. But the typewriter doesn't work. We saw in a previous episode that it had been extremely rewired, and none of the keys seem like they're connected up to the correct places. So we're kind of stuck in the water here. Yes, we executed instructions, but we can't go any further unless the typewriter's working. Or so I thought. I was kind of wrapping up the end of the day, and my dad was walking by. I said, "Hey Dad, come check this out." And so we fired up the Bendix G15, and I got it all the way through that boot up process, through these first 50 instructions, and I said, "It just ran 50 instructions. How awesome is that?" And Dad said, "What happens next?" And I said, "Well, the user of the typewriter is supposed to type in a number," and I type in 2, 3, or whatever. They're supposed to hit return, and then they're supposed to hit S. And I hit return, and I hit S, and the machine started doing stuff. And it continued to do stuff for like 10 minutes. And because I had already closed up the camera and I didn't think this was gonna happen, I unfortunately did not get that specific moment on camera, but let's turn the machine on one more time and I'll walk you through exactly what went down. And we're gonna watch this machine blink some lights and run some code. Okay, it worked once before. I have no idea if it'll work twice. Oftentimes getting things to work once is a lot easier than getting them to work twice. But hey, if it worked once, we can actually get it to work twice. So what we're gonna do is we're gonna do a full boot up, and then we're gonna just tell it to go and see how many of the tests it'll run through on the diaper here, because we actually got it to run through quite a few of them yesterday, and that was pretty exciting. So let's go ahead and hit the reset button here. The paper tape reader is going to kick off up here. We can see that the light kicked on. It's going to start reading in data. We can see that I've got the scope set up here with multiple things going on. So we can see the data filling in on the yellow line right here on the top. That is the first block of diaper. That's the first collection of test programs that need to run. We are now fully booted up, and so all that I need to do is flip the go switch on the typewriter here, and it should hit the typewriter with about 5 or 6 ones, and then go from there. Yep, it hit that. Now we've run a couple of instructions. We're reading in the next test program on the tape here. So we passed like a checksum, we passed all sorts of other things. It's read in that second test program on the tape, and now it's waiting for input from me. So we'll go ahead and hit a carriage return, then we'll hit S, and blinking lights are doing stuff. It's reading in more blocks of tape. And if we look at the scope here, things are changing. You can see it read in blocks of tape into M19 here. We've got the accumulator register. We've got, the accumulator register. That's doing stuff. Things are going crazy. And you can see that the blinking lights up here on the top are doing stuff. They're running a test. And then we hit a bell. So if you heard the bell, that tells us that that test passed, and we're reading in the next block on the paper tape up here. So we passed that test, we're on to the next one. We're up to like test 2 or 3 at this point. Every once in a while it's gonna hit the typewriter, and like it did just there, it's so wild. The blinking lights are going crazy. The whole thing is going absolutely bonkers. Down here on the scope, we've got M19 on the top. So M19 is anytime we read anything in from the paper tape, it's gonna fill up into here and then get copied out of here into various parts and run from there. We've got T0 in green. T0 is the sync pulse that we're using. The blue here is our accumulator register, and you can see it's doing all sorts of wild math in the accumulator register. Now the accumulator register is a short line, so it's looking like everything's repeated, and that's because we're looking at pretty much a full revolution of the drum, but we just got another bell. That's so cool. And then on the bottom here, we've got line 0. So anytime anything moves into line 0, this bottom one's gonna change, but really the bottom one doesn't look like it's changed all that much. We can see it's loading in another paper tape roll here, so we're on to another test. It's loading it right on in there. And it's just gonna sit here and run. Just sit here and chug away, running all sorts of different tests. Boy, every time it hits the bell, it makes me laugh. Every time the typewriter starts doing things, I'm mentally not prepared for it. This thing is absolutely, positively stunning. It's just sitting here running. And I was talking with Lloyd, and we're fairly certain that it actually makes it to the end of the diaper roll tape 1. That means that it will have successfully executed 75,000 instructions. I think it's pretty safe to say that we have a machine that rings the bell. That's another test pass though. But I think it's safe to say that we have the oldest running digital computer in North America right here in the shop in the middle of nowhere, Texas. It's all entirely possible because Bob is an amazing, absolute legend. It's really hard to get the words out when this thing's ringing bells and the typewriter's going crazy, but that's a good problem to have. If you guys haven't heard of System Source, go check them out. They're just stunning. And at some point in time next year, this machine, another test done, at some point in time next year, this machine is gonna make it all the way back up into Maryland at Bob's, and it's gonna be on display, and we're gonna be able to spin it up and let people use it. So we absolutely are not done with, it's gonna keep ringing the bell. We're getting near the end of the tape. This is the final test. So it's running a lot of really fast, short tests here, and each time it passes one of those really fast, short tests, it kicks that bell off. And you can see the blinking lights are going crazy. The bell is ringing like absolute bonkers, and we are almost at the end of the tape. You can see we've pretty much filled up this side and completely emptied out the bottom side here. We are nearing the end of diaper roll 1. Now, diaper is a 2-roll program, so eventually it's gonna ask me to install the second tape, which I don't have. We're gonna have to punch that out and put that in. I honestly didn't think that we would get this far, so it's just dinging like crazy. But there's a lot more work to do on this because the second diaper reel is going to test like division, multiplication, and we're going to get into those weird bodge wires that are going on the inside to try and figure out what the modifications were. And I got a sneaking suspicion we're going to butt our head up against that pretty brutally. So there is a lot more work to do, but I said I wanted to see this machine executing code by the end of 2024. That is a resounding success, punctuated by a nice little ring of the bell every time we do pass another test. You can see this thing is chugging along, passing tests with flying colors. The typewriter is still hot garbage, so that's what we're going to dig into next, so that way we can actually see what it's trying to type out, because right now it doesn't actually manage to type anything out. So that's what we're getting into next, but man, what a journey. What an absolute journey. This thing is amazing, beautiful. I'm just absolutely blown away by it as it's sitting here doing things behind my back. So we have a lot more to experience with this. I want to thank you all so much for watching, and I hope to see you in the next episode. That was job done. It passed all of it. Oh, that's awesome. Thank you guys so much.